Thermal cutting of structural steel. Welcome to another video on All About Bridges YouTube channel, where you can find unique informative videos containing bridge-related technical matters for free. In this video, we will discuss about the thermal cutting of structural steel. Cutting is one of the most important activity in fabrication of steel bridges. The flame cut process functions on the principle that a jet of pure oxygen is directed at a surface that has been preheated to its ignition temperature. The ignition temperature is the point at which the metal will ignite in pure oxygen. The material in the path of the jet is oxidized and ejected, resulting in a cut. The process does not function on all metals. The following conditions must be satisfied. 1. The ignition temperature of the metal must be lower than its melting point. 2. The melting point of the oxide must be lower than the ignition temperature of the metal so that the oxide can be ejected from the cut by the force of the oxygen jet. 3. The heat generated by the oxidation reaction must be high to perpetuate the cut, while the thermal conductivity of the metal must be low in order to contain that heat. These conditions are satisfied by structural steels. Flame cut, or oxy flame cut process, cannot be applied to metals which form oxides which are not easily removable. But it works for structural steel. Apart from above method, plasma cutting method is also used for cutting structural steel. In plasma cutting, gas is transformed into plasma when it is heated, which results in extremely high temperatures of up to 27,000 degrees Celsius being generated. The plasma arc cutting process severs metal by means of this highly constricted arc jet, which has sufficient energy and force not only to melt the metal, but also to eject the molten material. Because melting, rather than oxidation, produces the cut, plasma cutting can be used to cut any metallic material. It requires no preheat and produces minimal distortion in the material being cut. Plasma cutting has been in use for bridge construction for a number of years. Cutting speeds are relatively high, and the cut surface tends to be harder than the equivalent flame cut surface. In order to achieve a good quality cut, the following parameters require control. 1. The cutting speed. 2. The distance from the cutting nozzle to the workpiece. 3. The cutting nozzle size and condition. 4. The pressures of the heating fuel gas and oxygen, flame cutting. 5. The pressure of the cutting oxygen, flame cutting. 6. The power setting, plasma cutting. The overall degree of control of the movement of the cutting head is also very important. This is a matter that has improved greatly with modern CNC computer numeric controlled equipment, leading generally to a much squarer and more uniform cut than could previously be consistently achieved. Standards of cut surface quality is assessed in terms of squareness, perpendicularity, angularity, and depth of dragline, mean height of profile. However, these parameters are only appropriate to laboratory conditions, so the assessment of flame-cut surfaces on the shop floor is best achieved by having available samples which have been calibrated to the particular quality requirement so that they can be used as comparators. Figure 3 shows 3 flame-cut surfaces. The right-hand side shows the surfaces slightly weathered, and the left-hand side shows the effect of blasting with chilled iron grit. All 3 samples were assessed on their as-cut surfaces in accordance with the provisions of ENISO 9013, reference 2, for depth of dragline. Despite controls exercised on the matters listed above, the thermal cutting process tends to lead to the formation of draglines on the surfaces of the cut. A dragline is defined in BS 499, Ref 3, as serration left on the face of a cut made by thermal cutting, and the standard goes on to define drag as the projected distance between the two ends of a dragline, i.e. measure relative to a line square to the material surface. See Figure 1. When equipment settings are perfectly adjusted, it is possible to produce a cut with an extremely smooth and flat surface, where drag lines are not readily apparent, i.e., the serrations are very shallow, or the depth of drag line is small. However, Maintaining all the variables within the bounds that produce this standard on components of the scale encountered in bridge work is very difficult, and drag lines are usually evident to some extent. Individual isolated defects in the cut surface, such as gouges, see Figure 4, can occur from time to time. These are unacceptable in bridge work and should be dressed out by grinding to a smooth profile. Weld repair of such defects should only be considered as a last resort for deep gouges, and such repairs should always be subjected to surface crack detection after welding. This was all about the current topic. Tell us your topic in comments section on which you want to watch a video. Subscribe for more such content.